can assure you that coaching 9-year-olds and trying to teach them soccer is a lot harder than climbing an El Cap. So in case you're looking for your next activity. This topic's really special to me because during my time at AppsFlyer, I've had the chance to work on 4 independent implementations where we've worked on solutions to this problem. So I'm really excited to share it with you. First, a bit about me. I came to computer work in a somewhat circuitous path. Around 10 years ago, I moved to Israel and to do a postdoc at the Weizmann Institute. And after a few years of doing that, I was a bit lost a bit of interest in the research life. And on the side, I'd become very personally interested in the Clojure programming language and was going to the Clojure meetups. And at one point, AppsFlyer came to a Clojure meetup and said, "Hey, we're hiring." And I thought, "Ooh, that's a different thing." So I went and met with them and eventually joined AppsFlyer when it was quite small. I was the developer, around 12 developers when I joined, and it's been a great ride ever since. A few years ago, my wife got a job back in the US, so we moved back together, and so that's now how I live in Ohio, but I continue to come and visit Israel, and I really enjoy it. A bit about AppsFlyer. We provide a software as a service to cell phone app developers, and our main product is that we attribute advertising for cell phone applications to the actual installs on the cell phone. And then for the life of that install, we continue to collect data. And I personally work in the data analytics team, and our job is to take this large stream of data that's coming in from the cell phones and aggregate it and produce dashboards for the clients. So most of the examples that I'm going to show you are going to be from there. But as I'll try to explain, I don't think the principles that I'm talking about are really all that specific to advertising. This is the outline of our journey. First, I'm going to explain what is cardinality and then why should we care about it. Then I'm going to talk in general about limiting cardinality, and then dive into some specific implementations for limiting cardinality, both in a batch job and in a streaming job. But if you don't take anything else from this talk, I'd like you to start thinking about the cardinality of your own data and how it affects the aggregations that you might be doing with it. What's cardinality? Couple of ways to look at it. So on the top, we have a set that contains the items A, B, C, and D. The word cardinality comes from set theory. So these vertical bars, that means cardinality. So this set has a cardinality of 4, which of course is a fancy way of saying how many distinct items are in the set. I guess we, or I like to be pretentious, so we're going to use the word cardinality a lot, but it's not a particularly difficult concept. So why do we care? So like I said, at AppsFlyer, we're taking in a stream of events, and I've just drawn some very simplified events here where we have an event from campaign A in a particular country, the United States, and it's got this timestamp. And then there's more events from perhaps other countries and other campaigns. So in our case at AppsFlyer, we're getting, I think last count, 200 billion of these events every day. So if I try to create a dashboard that goes over those 200 billion events and shows something meaningful to our clients, it's not going to be interactive. So what we do is sort of the obvious thing. We aggregate the data, in this case to daily granularity, so we won't know exactly when each event happened, but we'll know how many events happened per day. And so here we can say now that the campaign A had 4 events that happened in the US on this particular date. So this is great. Everything works wonderfully until something is wrong with the data. So in our particular case, the thing that often happens is these events start off as clicks from our clients, and they have various macros that they put into the click URLs. And if they're editing these clicks in Excel, these are clients, and they drop the macro in the wrong spot. And so now we have a user ID right in the middle of the campaign field. So now what happens, we try to do the aggregation, and instead of getting a nice small table with just a few rows, we end up with a huge table. So I've got this A ... You know, this client might have had millions of broken campaign links, and so now what used to work well for us is not working well at all. The database is full of all this garbage campaigns that this client sent us. The queries we're running on the database are going nowhere because we're back to the raw data. For this client, we're essentially running over their raw data. And so very early on, we realized we needed to do something about this. And so what are we going to do? We're going to take dimensions that are susceptible to this problem, and we're going to limit the number of distinct items that they can have. So how are we going to do that? The first thing we tried to do, and this is actually what we did, I'll call it the dumb cardinality limit. We simply start a list every day. And so let's imagine this table on the left are the events in order from a particular client. We start filling the list of allowed values for that client at the beginning of the day, and then once we hit the limit, we don't accept any more values. And then everything else goes into a constant here, which we're calling exceeded. So that works great from our perspective as data analytics team, but for the client, it's not so great, right? They have these other 2 campaigns, campaign C and campaign B, and you can imagine others, and they don't get to see them anymore because they had this bug where somebody dropped a UID in. So what does the client really want us to do? Well, they would much rather that we figure out what are the non-broken campaigns and try to show them those. So the way that we could imagine doing that is we'll take the data for this client, we'll sort it by some priority. In this case, the priority is just how many items, how many events we saw from that client. But you know, you could have your own business priority here. And then we'll just cut this list off at however many items we want to allow. And so this is just showing we cut it off, and then everything below the line that we cut off, we map those to the exceeded value, and now we're back to a good table. This will fit in our database. Queries will run interactively against it, and the client will be pretty happy. They lose all the A campaigns, but they probably didn't really care about those anyway, and they'll get to see their good campaigns. So now we're going to dive in and look at how do we actually do this in a batch setting. In our architecture at AppsFlyer, we have a large Druid that's holding historical data, meaning anything that arrived, say, a day or two ago. And then for the data that just arrived in the current day, we're streaming that data into Quickhouse. And at the time that we set this up, we felt like we understood how to handle the problem of reducing the cardinality of the batch data. And so we went ahead and addressed that. And for the streaming data, we didn't know at the time how to handle it. So, and it's only one or 2 days. So we felt like we could tolerate it, although it still causes us some pain. And so that's why we initially worked out how to do this problem in batch. And so I'm not showing it here, but we had an initial implementation that kind of did both the data aggregation and all the cardinality limitation all in one go. Eventually that didn't work very well. But stepping back from the problem and applying what I think is sort of the most valuable principle that we have is to try to tease apart your problem into multiple different concerns. And that turned out to be the key that let us solve this. So what we were able to do is split the problem out into one job that finds the allowed values for clients, and then another job that converts those values to a constant and aggregates away the excess. So rather than trying to shove it all into one crazy SQL query, we're gonna split it up. So how are we gonna find the allowed values? It's basically what I showed before, where we take the data for a client and order it. But here I'm showing how we can do that for many clients at once. And we're gonna rely on window functions in SQL, which a lot of you are probably familiar with. They're not exactly an advanced part of SQL, but they're definitely maybe not the first thing that you learn if you're using SQL for regular app development. So I'm going to walk you through one because I think it's actually kind of interesting. So there's a inner query here, which is the part with the from. And so on the inner query, we're going to select the client and the campaign, as you might expect, but then we're also going to select the row number. And then over here says we're going to introduce a window into our data. So if you imagine our data is like a big, long Excel sheet, we're going to cut it up into windows, one window for every client. So that's what I mean by here, partition the data by client. And then within each window, we're going to order it by the count. Once we do that, then we're just going to look for each row and say, where are you in your window? Are you the top? If you're the first item, you get row 1, if second item, row 2, and so forth. Once you've done that, then we can have an outer query where we just filter and we say, okay, we don't want anything where the row number is more than some constant. In this case, I'm using 1,000, but it can be whatever you want. And so with this window query, that essentially allows us to get the values that we want to keep for each client. I'm not going to go into it here, but if you run this and one of your clients has the problem with the user ID in the campaign and maybe their window has 1 billion items in it, this query is actually going to explode because in Spark, at least, what it's going to try to do is partition your data by client ID, and one client will now have 1 billion items and everybody else has 1,000. And so this query won't work as I've written it here, but I gave another talk that you can look up where we show how to use something called salting that gets you around that problem. So back to the main flow, where now we collect a small table where we have the client ID as one column and whatever campaigns we're going to allow for that client are in another column. And now it's fairly straightforward. We're going to join our aggregated data with the allowed list for that client, and then we're going to obviously join by client ID. And then for every row, we're going to check, does the campaign, is it in that list that we're allowed to keep? If so, we get to keep the campaign. Otherwise, it goes to the constant value exceeded. That all works pretty well, except we need a way to do this also quite efficiently. And so what I've shown there, in Spark, the default way to do a join is a shuffle join. And I suspect a lot of you are probably familiar with this, but if you're not, the intuition is that Spark will take your data and it will spread it out on the cluster, moving each client's data to a different machine on the cluster. And then it's also going to move the list that we're joining to in the same way. The downside of that is that it's read all your data and shuffled it all over, so there's a large I/O cost. And in this case, we can do some tricks to avoid that cost. And so what we're going to do is something called a broadcast join, but it relies on getting the allow list table to be very small. And so there's two tricks that I think are pretty cool that we're going to use. So first, if the client doesn't have a long list of values, if they haven't exceeded the limit, we'll just not put that client's row in the table that we broadcast. And so if you're not in the table, that's a signal you get to have whatever values you have. And the other even more important optimization is that instead of shipping the strings out in this list of allowed campaigns, we're going to hash each one into an integer. And of course, an integer is much smaller than a fairly long string, and so this saves an enormous amount of data. So then we're just going to compare the hash of the campaign with the hash of all the campaigns in the allow list. The part that actually makes this work well is that if you do have a hash collision, which is definitely possible, although rare, that just means that the client will get one more campaign than they're supposed to have. So it doesn't hurt them, doesn't hurt us, so we save a bunch with these optimizations. All right, now back to the straightforward part. So you see here for this client, we've taken their campaigns, and for most of the bad campaigns, we've mapped them to exceeded, and then we aggregate them away, and we're left with, again, what I hope is a small table that's going to get the job done in the database. So this was all great and works pretty well, although we're still exposed to high cardinality in our streaming area. And furthermore, as part of other interests in the company, we wanted to move away from using Quickhouse. I guess the two major things that are difficult with Quickhouse for us is that Quickhouse is stateful. So when you give data to a cluster of Quickhouse machines, it stores the data locally on its disk. And so if you lose those machines due to some user error or hardware failure, then you lose your data. Whereas with Druid, Druid's essentially stateless. So the data's stored on S3, you can delete your whole cluster, turn it back on, it'll go get the data back from S3 and you're back in business. So if you work in a cloud like we work in AWS, it's a much more comfortable place to be. And also, I guess a side benefit is we work with Clojure and Scala, and we have a lot more JVM experience. So Druid's written in Java, Quickhouse is written in C++, so it's easier for us. And also, we suspect that Druid's a little bit more sensitive to high cardinality data, since it's really intended to be a data store for aggregated data. So how are we going to handle the situation in streaming? So first off, to explain, we're going to use Spark streaming, which is not really streaming. We're not going to get one event at a time. Instead, we're going to get, in our case, fairly large chunks of data. So if you can imagine, this blue line's our data stream. Spark is going to give us a data frame, which is its term for the internal chunk of data that you get. It's going to give us one of those every 10 minutes, and then you can essentially do whatever you want to that, just as you would do in the batch situation, and run all the SQL that you want to run on that. But the problem here is we're only going to be looking at 10 minutes, and I don't know from that 10 minutes which values that the client is allowed to see. I need a longer look-back window to decide. Remember, in the batch case, we're doing a whole day together, so 10 minutes is not enough to decide, oh, these are the top campaigns. And kind of a side point is we don't really want campaigns jumping in and out of the list of allowed values, right? Because we want the data to be somewhat stable over the day. So how are we going to do it? We're going to take the same steps as before. We're going to find the allowed values, convert them to a constant, and aggregate away the excess. The only difference here is going to be that we have a different way to find the values that we're allowed. So to do that, we're going to leverage an approximate data structure. And the implementation comes from this really excellent Apache data sketches library. I highly recommend everything that they do. They have a lot more that I'm not presenting here. But the sketch we're going to use is called the top items sketch. And it's going to provide an approximation of the most frequent items in a stream of data that you provide it. So what we're going to do every 10-minute chunk is write one of these lists out somewhere. And in our case, we're going to write it out into a table on S3. So now we have, for all time backwards, these little small chunks of approximated top items. And before I show you what we'll do with that, I'm going to try to give you an intuition for this sketch because it's kind of cute and somewhat easy to think about. The data sketches library uses a sketch called Misra-Grease. I'm not sure I'm pronouncing that right. I'm going to show you a variant of that that's called the space-saving algorithm. It happens to be easier to explain, but they're both roughly equivalent. So what you have here is conceptually a linked list of some length. In this case, I'm showing you 3, but in reality, it would be a few thousand if that's what you were going to try to accumulate. And it's going to be sorted by count. And so here we load the first 3 items into this list. And then we get to the next item, and this is where the sort of the magic of this algorithm is. So you can imagine, instead of taking the last item off and just putting the C on with the count of 1, you're actually going to pop the last item off, put the C in, but you're going to give it the count of whatever the item had there plus 1. And the reason for that is if you have an established list, you want a way for new items that come into the stream to make their way up the stream. And so if you always just inserted them with count of 1 on the end of the list, they would always just get kicked off by the next item that was in there as well. So this way, whenever you introduce a new item to the list, you give it a boost. It says, hey, I'm going to give you a chance to rise up into the list, and if it falls back down now, that's its own fault. It can handle that. So then we continue with that rule. So when we get another item, we pop the last item off, we pop it in, and instead of a count of 1, we give it a count of 2. Same with B here. And then finally, for these items that we've already seen before, we just increment their counters as you would expect. And so the outcome of this is that you've got the top items in your stream of data, and you're only holding a few, maybe twice as many items as you want to look at eventually. Whereas if you were to say accumulate the distinct count in that whole window, it could be enormous. The final step is that these top item sketches are all mergeable. So I can take one from one 10-minute period, pop it onto another one, and get the top items for that 20-minute period. And so I can say, oh, I want to look at the last 24 hours, accumulate that into this list of allowed campaigns. And so from that, I can derive the same list of allowed campaigns as before. So I'll remind you then, the other steps are just going to be the same, right? For every 10-minute batch of data frame, we're going to join with the allowed values and throw out the ones we don't want. So far this has been working really well. While we're streaming data into our test environment that we've been working on, I can see easily 40% reduction in the number of rows of data that is going in. This hopefully will get us on track to replacing Quickhouse with Druid, make our stack more cohesive and also a little safer. And perhaps even more importantly than the total number of rows in the database is we want every query to the database to be somewhat similar in terms of response time, right? We don't want one query to take 10 milliseconds and another query to take 5 minutes or something. And that's what you get if you have these huge outliers where one client has filled up 10% of the database with their garbage data. And then I think the main takeaway for you all, if you don't get into the nitty-gritty of this specific implementation, is to think hard about the cardinality of your data, right? Anytime you're trying to aggregate data to make it more accessible or smaller, you need to think hard about what's the cardinality of every column. And then hopefully you'll end up with a nicely packed suitcase and a good happy database. So I want to especially thank the organizers of this conference, and both for putting on an awesome conference and for all the coaching that they gave us, and thanks as well to you all for listening.